We're going to talk about Le Chatelier's principle. Le Chatelier's principle starts with a system that is at equilibrium. Let's talk about the Haber process in this system. We are supposing at this point in time that we have taken the initial concentrations, let the reaction proceed until such time as the forward and the reverse reactions were having the same rate, and at that point we were at equilibrium. Le Chatelier's principle says once we find equilibrium, if you stress this system, the forward or the reverse reaction will change to undo the stress. How can we stress the system? We can change the concentration of the reactants or products. We can change the temperature at which the reaction is occurring. We can change the pressure. All of these, depending on the reaction and its thermodynamics, will change the stress to undo it. Okay. The way that a system can compensate, it can shift the left to make more reactants, which in turn uses up products, or it can shift to the right, using up reactants to make more products. If a concentration is changed, it will shift away from the added component to decrease the amount, or if you remove a product or reactant, it will shift towards that component to make more to regain equilibrium. What you must know is when equilibrium is re-established, the absolute values, the absolute concentrations may have changed, but the ratio of the products over the reactants remains the same as the original equilibrium. Here's, to put a fine point on this, I spoke earlier, when you change the pressure, it can affect the equilibrium. However, an inert gas does not affect the equilibrium of the system. If the volume of the system is decreased, the system will shift towards the side with the fewest number of moles. That is because the volume is decreased, there's less space, it will go to the side that has the fewer number of moles, therefore the fewest particles, to regain equilibrium. Temperature is the only stress to the system that would change the value of KEQ. Changing the concentration, changing the volume will not change the value of KEQ. If you add energy to a system, remember you're adding energy to the entire system, and it will shift away from, if you add heat, shift away from the side, either the reactants in an endothermic reaction or the product in an exothermic reaction, to compensate. All right, here we have a reaction. Looking at it, it is balanced. I see that this is the solid, this is the solid. These are gases. The equilibrium expression for this would be this. Okay. If you added carbon monoxide, if you made this larger, you would disturb the equilibrium. It would shift to the left, using up more carbon monoxide to undo what has been done. Add carbon monoxide, shift to the side that uses carbon monoxide. That would be this. Remove carbon or tetraarsenic hexoxide. These are both solids. They are not in the equilibrium expression. Therefore, this will not shift the equilibrium. No shift will take place at all, will not stress it. The removal of gaseous arsenic, if we take this away, then it will shift, the equilibrium will shift to the right to make more of this to replace it. Too far. Okay. All right, let's look at Let's look at another exercise. All right, predict the shift in equilibrium that will occur for each of the following processes when the volume is reduced. On this side, we have 6 moles of gaseous reactants. This is a solid. And on this side, we have 4 of a liquid. So when we change the volume, we will shift to the right, to the side that has the fewest number of moles. In this instance, we have 2 moles of gaseous product versus 1 mole of gaseous product. This will again shift right because 1 mole of the products has 6.02 times 10 to the 23rd molecules, while this side, the 1 mole here and the 1 mole there, has 1.204 times 10 to the 24th particles or molecules. So it will shift to the right to the fewest side. Now here we have 4 moles of gas on this side and 4 moles of gas on this side. When we shift, there will be no shift because there's no advantage. It will not go to, they have the same number of particles. So there will be no shift here. Okay, so this is asking us this time for what happens to the value of the equilibrium constant. Delta H is 181. That is an endothermic reaction. So why don't we just think of the enthalpy as a reactant. So we are increasing the temperature, so equilibrium will shift to the right. The equilibrium expression for this reaction looks like this. Right? When we shift this to the right, we are making more of the NO, and there is less of the reactants. So, simple math, the numerator is larger than the denominator, so the Ke value will increase. On this side, this is an exothermic reaction, so we can think of the heat as a product. Please remember, we're heating the entire system, not just one side. The equilibrium expression for this equation looks like this. And when we heat it up, it will shift to the left, away from the heat, where heat is absorbed to this side. That means that the denominator will get larger, while the numerator will get smaller, so the value of KEQ will decrease.